I have good news and bad news.
Let's bad news first.
I forgot reading this, like, I didn't even see this question.
The good news is
I didn't see a question.
I lost 6-2
Yeah, I got the same.
in my tennis match last night, and then I won 6-1.
Is that the good news?
What is your tennis?
And we only played 2 sets.
Did you bet money on it?
No, I don't do that. I can't afford that. I lose most.
No, this is what you do.
So that's-
Hey, I bet you're gonna win.
That's the good news.
Any bad news?
I caught a bit of a cold.
Oh, no.
Well, I'm standing back here.
Oh, sorry.
I feel pretty good, but my voice is a little rocky. So, question 1 is straightforward left recursion. Question 2, you've got to do substitutes. I better find a quiz. Thank you. Question 2, you've got to substitute E into F. And then you got to substitute F into S. And then you can remove the left recursion. On several of yours, I circled, and circled. And so I circled the F, and then I circled the E, and then I circled the S that says you've got indirect left recursion. So you gotta
Really?
you gotta fix that.
Oh. Indirect.
On question 2, to simplify, C, so S goes to ASA, BSB, or A or B, that's all good. So I can get S goes to ASA, and then that S can go to A, so I can get AAA. So S is able to generate a terminal string. But if we look at C, C generates AC or CD. The C can't ever generate a terminal string. It's always generating another C or another D. So I pitched the C. And as a result of pitching the C, A, B, D, and E are all unreachable. And so the final answer is S goes to ASA or BSB or A or B. The leftmost derivation, I don't think anyone missed. The parse, or the parse tree, I don't think anyone missed. Why are ambiguous grammars undesirable? I gave credit for almost anything there. They're undesirable because you get 2 parse trees. The parser captures the structure of the program. And if you have an ambiguous grammar, you have 2 parse trees, so you have 2 structures, so the grammar has choices, and in general, not good. Problem 6 is ambiguous. If you showed me 2 parse trees and then quit, you didn't answer the question. And so I gave credit for 2 parse trees without an answer now, but on the exam next Thursday, I won't. You still got to answer the question. 2 parse trees show it is ambiguous. Okay? 7, only a few of you got, and it is a computability and automata question. So in computability and automata, you learned regular grammars are equivalent to finite automata. Non-deterministic finite automata is equivalent to deterministic finite automata is equivalent to regular expressions. You learned that all of those things are essentially representing the same language or the same thing. You also learned that deterministic push down automata are not equivalent to non-deterministic push-down automata. If we think about palindromes, a palindrome is a Toyota. A deterministic push-down automata can recognize this palindrome. Why? Because it has a middle marker. So it knows C and A, push an A, C a T, push a T, C and O, push an O, C a Y, stop pushing. C and O, pop an O, C a T, pop a T, C and A, pop an A. C the end, the stack's empty, it is a palindrome. Make sense? You with me? If I have A, B, B, A deterministic push-down automata cannot recognize that palindrome. C and A, push an A, C and A, push an A, C a B, push a B, C a B, push a B, or not. C and A, push an A, C and A, push an A, C an empty, oops. I didn't recognize it. I don't know when to stop pushing and start popping to match the palindromes. You with me on what I'm saying? We recognize a palindrome by pushing onto a stack the front part and matching it to the back part by popping the stack. Here, I don't know where to start pushing and stop popping and that stuff. So this can be recognized by a deterministic push-down automata. This could be recognized by a non-deterministic push-down automata because we do them all at one time. Non-determinism essentially gets you infinite parallelism. And so push an A, pop an A. All right, well, not done, so that didn't work. So push an A, pop a B, well, there's no B to pop. Well, so that didn't work. Well, so the point is, a non-deterministic push-down automata tries all of the possibilities all at the same time. That's what the non-determinism gets you, essentially infinite parallelism. There is no conversion from deterministic push-down automata to non-deterministic push-down automata. Again, you learned that in computability on automata. We argue you should have, I like to argue, right? We established that Tuesday. We argue you should have learned that in computability and automata. No?
He did not ever, I don't think he ever lectured on the difference between deterministic and non-deterministic CFG or pushdown.
Yeah.
We've
I
basically,
assumed that we would know.
he established that there does exist a DPDA, but we never, besides declaring it existed, we moved on straight to
It's in the
non-deterministic.
textbook.
Well,
Yeah, that's what it is.
Now we know.
Too late now.
too late now. So it cost you a point.
Yeah. So we go to Buenos
And
Aires for this.
so this is a small price to pay to earn the 4 or 6 points on the exam in a week that asks you the same question.
So what's the correct answer?
Well, so I'm getting there. So we learned
You should have.
a topic of computability and automata is
There we go.
the fact that context-free languages generated by context-free grammars are equivalent to non-deterministic push-down automata. You talked about context-free grammars are equivalent to push-down automata. Whatever a context-free grammar can generate, a push-down automata can recognize. All context-free grammars may require a non-deterministic push-down automata. Okay? So, non-deterministic push-down automata can recognize anything a context-free grammar can generate. All right. So, how is this relevant for you in this class? Well, your parser is the implementation of a deterministic push-down automata. And so your parser is equivalent to a deterministic push-down automata. A deterministic push-down automata. That's what you're implementing. Which means that if you create any old context-free grammar, it may not be parsable by our techniques we're learning, because the techniques we're learning are the implementation of a deterministic push-down automata. So, all context-free grammars can be recognized by non-deterministic push-down automata. Okay, that's a hint, that's instructive. But programming languages are translated into binary by deterministic push-down automata. Okay, well, that too is instructive. There's no question there. What impact does this have on the construction of the grammar that defines a programming language? So the question's got deterministic push-down automata, non-deterministic push-down automata, and context-free grammars all in the question. The answer requires you to comment on the construction of, or the relationship of, context-free grammars to push-down automatas. And essentially, you should say context-free grammars are equivalent to non-deterministic. So the context-free grammar that we use must be a subset of all context-free grammars recognizable by deterministic push-down automata. That's essentially the answer to the question. Well, and so you all apparently got together a little on this quiz, because half of you wrote something like, not all context-free grammars are good grammars, or something like that. I didn't read it too carefully because I just counted it wrong. Yeah, good grammar does not mean good implementation for compilers. That's what half of you wrote. And so, well, that's okay. I mean, I wanted you to do the quiz by yourself, but I'm not upset with that. But I am not accepting that answer because in a given circumstance, I might create a grammar and a compiler that works. I'll force it to work. I'll make it work. I'll let it back up. I won't use the compilers that exist. And so I'll get to your grammar. So we know about GCC. Yes, you know about GCC. It compiles. GCC is actually a script that includes the assembler and a compiler and a variety of compilers actually. It'll compile C++ and so on. So GCC is a compiler. It used to be an LALR compiler. You will learn in another 3 or 4 weeks what an LALR compiler is. We do that. About 5 or 6 years ago, they rewrote it as a recursive descent. They rewrote it to do what you're doing for C minus. The compiler that you run on GCC now is your compiler for all of C. Well, all of C isn't a top-down nice grammar. And so they went in and they did a bunch of stuff you're not necessarily supposed to do to make it work. They went in and did things that you all aren't in general going to do to make it work. But they figure it's faster and better, I guess. And so the point I'm making is, even though you've got a nasty grammar, you can sometimes make a compiler for it, which is why I rejected that answer. And besides, you all need to realize this first. That's fairly important. And you need to realize this. That's fairly important. And you need to realize what you're doing. And what you're doing is this, for a subset of these. And so while it has no implication on the compiler you're writing, and that it's general knowledge of what we're talking about. And you need to understand that. And so I put it on this quiz. I put it on the exam next Thursday. It counts 4 points there, it counted 1 point here. Everybody will get it right now, so it won't cost you as much. Brenda?
What symbol is that?
This is the subset side.
It's a subset, okay.
This is, one is a subset of 1, 2, 3, right? So it's a subset side. Salim,
Yep. How much did those guys get paid?
how much what?
Did those guys who made the compilers for C
I'm gonna, sorry. I got a little cold. My head's plugged up terrible.
How much did those, the guys who recreated the compilers for C get paid?
Well, I have no idea. This is, I kind of like this too. This is pretty cool. This is from GNU, which is the Free Software Foundation, which I think gets or has gotten federal funding. They may not anymore because there's an onslaught toward education, but that's another thing. And so these people did it. And I expect they didn't get paid much. I mean, I have no idea. But I like this. Everything in computing's an acronym, right? And you've heard of GNU, right? They provide free software. You know what GNU stands for? It stands for GNU is not Unix. And so it's a recursive acronym. I like the idea that it's a recursive acronym. Now, why they don't want it to be Unix, I mean, I don't know. But that's what it says. Yeah, so I'm passing this sheet around. Dr. Umapathy has a graduate student. His graduate students do human subjectivity on stuff. They create websites and then they have people use the websites and see how good they feel about it. And so his graduate student is seeking people to test the website. And this is the blurb. If you were willing to volunteer, then do whatever this says. And so you can look at it, hand it around. I got an email and I promised I would share it with you all. Everybody has seen it? Everybody who wants to see it has seen it? All right. Question 8, I think I did for you. Question 9, it's not unlike question 1. S goes to A, who goes to F, who goes to S, and so you gotta make substitutions. I thought I'd give you another shot of that. In case you missed question 1, I was hoping maybe you'd find it in question 9. I don't know if you did or not. Question 10 was almost like the one on a previous quiz. 1, 2, and 3 is the start state, then it goes to 2, 4, 1, and 3 and stays there. So there should be 2 states. Left factor, so you gotta left factor the A out of AB and AC. You gotta left factor the little a out of AB and AC. You gotta factor the B out of AB, BA, and BC. Whoop-de-doo. Francisco?
10 looks like again.
I'm sorry?
Tasha, number 10 looks like.
Number 10.
That's minimized. And so we claim that you should get to 1, 2, and 3. And then on A and B, you should get to 1, 2, 3, and 4, and stay there on A and B. And I will do that for you if you'd like. Anyone like? Kevin?
I just wanted, you said minimize, because I think it's changing to deterministic. Because, yeah. But it is, but it does only have to.
It's, yeah, it isn't minimized, it's convert non-deterministic to deterministic.
But it is minimal though, because it has,
Yeah, it's gonna be minimal too.
it has the start state and the except.
Yep, yep, and so it's not gonna shrink any more than those 2 states. Eric?
On number 9, you said that you should only make left recursion with no unnecessary modifications. When I was working on this, that really confused me, because that was just like his simplification. And also Slate, I was working with Slate, he also did about that too. So this is the wording that confused me. I just assumed.
Only eliminate left recursion, make no other modifications. Well,
Basically do what's necessary, not.
well, but I'm not eliminating left recursion if I don't make the substitutions, because otherwise I've got indirect left recursion. And so I've got to make those substitutions in order to eliminate the left recursion. What I didn't want you to do was to put in W for B, the little w, and the little b for D, and those kinds of things. But you've got to do the substitutions in order to eliminate the left recursion. Uchi? Uchi? Okay? Okay, okay.
Number 11, how did you, like you said, eliminate the terminals and the non-terminals from the left factoring?
Number 11, how do you eliminate left recursion?
Factoring.
Factoring. Number 11, how do you eliminate left recursion?
It doesn't say eliminate, it says
No, erase it.
This is how we talk. Because that would be this one, all you're doing is making substitutions where necessary. Make that higher.
I think Eric maybe went to get one.
There's one upstairs in the.
Okay?
That's the one that took me off here.
We need to further eliminate B, left factor B in rule X.
I'm sorry?
In rule X, the variable B, the rule B in X, just create those to AX and then
Or
it
C.
goes back. Could that be factored out as well?
Yeah, you would make one more substitution.
Yeah.
But you could substitute B or the C.
Yeah.
The C terminates as a B,
Yeah.
B terminates by B, and C is.
Well, sure, I mean, I could substitute this in for B, but that's not a left factor issue anymore.
Oh, okay.
That's just another substitution.
Okay.
So it's no longer.
Wait, so it's the X rule, X goes to terminal B or C, or non-terminal B or C. That's, we wouldn't need to make a substitution to make it left factor?
Oh, no, we should quit it at this point. The question says left factor, so that's all you do.
Okay, so is X going to be?
I mean, we could make a ton of other grammar modifications to make the grammar look more pleasing or arguably more efficient. You may not have talked about this. In computability and automata, they talk about these as unit productions, where a single non-terminal is replaced by a single non-terminal. In general, that's not desired, because that makes the compiler do some work and it doesn't buy you anything. So typical grammar simplifications might involve the removal of unit productions. But that's not what the question asks for. The question says left factor it, and doing anything else beyond what I've shown here is more than just left factoring. Okay? Good?
Can you do number 9?
Did I do it? I think I can do all of these.
Will you?
Oh, not the right.
Oh.
Well, I turned over, but yes, it was wrong. So I put the check mark on turning over to show you that I saw it turned over. I gotta do which one?
9.
Now, I claim I can do them all. Now, I may not do them right to begin with, but I got 40 of you nearly to watch me, and you tell me if I do it wrong. So 9 has got S goes to A, B, or SD, or A. A goes to FM. F goes to SX or B. B goes to W, D goes to B. Okay? So I got left recursion immediate. Well, whoop-de-doo. Whenever you have these, A goes to F, F goes to S. Ooh. and I want to fix the non-immediate left recursion. Because I got to do immediate left recursion after I fix the non-immediate. So I want to do the non-immediate stuff first. So I'm going to rewrite A goes to SXM or BM. So if I put F in here, I got to put both of F's in there. Or I can't throw away F. Now I do have a choice on that. I could write it as A goes to FM or SXM and keep F goes to B. So I just put this one in. But if I just put this one in, then I got to keep the original one and add this one, which I put in. So I got a choice. I could do it like this, or I can put them both in and throw this away. Thank you. Make sense? Now, when I grade these, it drives me crazy because I actually work the problem through. I look at what you did, what you did, what you did, what you did, and see if it works. Because you have a choice, and both of them are correct. All right, I'm going to do this. And so I don't have this anymore now. I just have this. And I got this and I got this, okay? So now I'm going to put in S goes to A, who is XMB, or BMB. See, again, I got to put them both in for A. And if I'm going to throw out A, I got to put it in for A everywhere. So if I had an A down here someplace, I'd have to put A in down there as well. If I'm going to throw A out, I got to put it in. So I've got all the choices. And so who stole my eraser? Where did you find it?
They don't even stock them upstairs anymore. They said it's too old school. They only have them for dry erase boards. So I stole from another room that's on the other side of the wall here.
Yeah, that's what I would have done, is walked into the next classroom and
Well,
helped
I didn't want to
myself.
steal it from the classroom, then somebody else later is going to have to steal it from
Well,
somebody else too. So,
We expect there's one eraser for every classroom at least.
yeah. we
So if I
pretty much-
went into the next one, they should have two.
Probably
And I'll
have
take
about 2 of
one.
those erasers for the whole building.
Yeah. You know what I want? 40 years ago, when I taught with chalkboard, I had an eraser that was this long. And it was curved. So I could push in the middle of it, and erase it. It would erase it good. I mean, what is this, 6 inches? It was twice as big. I could erase twice as much. I want one of them.
I bet they have them online.
Yeah, go on Amazon, see if they got a foot-long eraser. Amazon's got everything, right? All right, so I got this SD or A. So now I don't have this anymore, and I don't have this anymore, and I have this. Yes?
Yes.
See how I got that? Yes, yes? Well, so now I've got beta, A alpha. So I get S goes to B, M, B, S prime, or A, S prime. S prime goes to X, M, B, S prime, or D, S prime, or empty. And then I still have B goes to W, and D goes to B. And so this is my final answer. And so that was a good question. Whoever asked for that, that's something something we may not have done exactly before. Jeffrey.
That's right. Not to take us backwards, I had a question sort of about number 7 again.
A question about what?
Number 7 again?
Number 7?
The DPB, equivalent to DB.
Okay, what about that?
So why is it that the parser that we're making like a deterministic push-down automaton?
Because we're writing a deterministic program. We don't have non-determinism on a computer. Computers do not execute non-deterministic machines. Our computers are all deterministic. So we're implementing a deterministic push-down automata. We arguably could implement a non-deterministic by allowing it to back up. If it parsed the ways and found something it didn't like, it could back up and try a different path. That would be a way of doing a non-deterministic parser. Okay? But it's conceivable, well, and not unrealistic, that the parser has to parse 10 million line programs. And so it takes it a long time to parse those programs deterministically. And again, the parser is trying to capture a unique structure of the program so that it can do the other checks. It can generate, it can test for semantics, and it can generate intermediate code. So all of the parsers that exist for general purpose programming are deterministic, which requires the grammars to be context-free grammars that can be parsed by deterministic machines. That makes sense? That answer your question?
So you're saying that it's more a consequence of the convention of writing compilers?
Well, it's,
Not so much limitation of the fact that we're writing programs on conventional computers.
well, I think it's a consequence primarily of the fact that we need something that's relatively efficient and it's being run on deterministic machines.
Okay. But like technically speaking, our machines, you could have a deterministic Turing machine, and that does more than a deterministic pushdown automaton, right?
For sure.
So our modern computers are effectively, they can do the same as deterministic Turing machines, right?
Well, it turns out non-determinist, well, Turing machines, so
And I know that non-determinism doesn't get you anything in Turing.
well, so this is really computability and automata stuff again.
Yeah.
And we're talking about now the concept of what can be computed. And so the Turing machine captures the concept of what can be computed. And so I don't know, I used to teach computability and automata, which I had fun with that. So there's 3 kinds of problems in the world. Okay? Just 3 in general kinds of problems in the world. There's those kinds of problems for which no computer program can be written. There's problems for which a computer program can be written, but the computer can't compute them. And then there's easy problems, like compilers and sorting and searching and those sorts of things. And so I'm talking about polynomial bound algorithms, or algorithms that can be run by a deterministic Turing machine in polynomial time, or algorithms that can be run by a non-deterministic Turing machine in polynomial time. And so you talked about P and NP in computability, and so searching, sorting, those sorts of things can be executed by a deterministic Turing machine in polynomial time. Polynomial time is anything like n log n squared, n cubed. Those are all polynomial time. 2 to the n is exponential time, and that doesn't fit. And so NP stands for problems that can be executed by a non-deterministic Turing machine in polynomial time. Again, that's what you learned in computability and automata. Problems that are NP are roughly all equivalent, and they exhibit exponential growth. And so famous problems are traveling salesman problem, bin packing problem, NatSat problem, canonical satisfiability problem. Those are famous NP problems. Actually, NP complete, but that's another issue. Okay? And so what we have is we have city 1, 2, 3, 4, 5, 6, and we've got roads between them all. So there's a road between every city. I probably didn't draw enough lines. And so the traveling salesman problem says, I want to start out in any city, and I want to visit every other city exactly once in minimum distance. And so I've written this program. It's not a horrible program to write. You can write it. And I ran it for 5 cities. I bit my lip. Run it for 5 cities, spit out the answer perfect. Ran it for 10 cities, hesitated for a while, spit out the answer. Ran it for 50 cities, it's still running. And I wrote it 35 years ago. It would be still running, but I wrote it at the University of Nebraska. And
So it's still right there.
the computer broke before my program finished. So what do? You start out, all right, I want to start out in city 1. I want to go to city 2, I want to go to city 3, I want to go to city 4, I want to go to city 5, I want to go to city 6. Well, if I go to 2, then I want to go to 3, then I want to go to 4, then I want to go to 5. I can draw the tree, and the tree explodes. But then I got to draw all of the trees. I want to start out at city 2. I want to start out at city 3. And I want to go to 1, I want to go to 3, I want to go to 2, I want to go to 1. And I got to look at every one of them in all possible combinations. So the amount of work that has to be done explodes. Got 5 cities, it could explode and still do it. 10 cities, it could explode and still do it. Got 50 cities, it'll explode and can't do it. They talk about things, I love this. They talk about more computing time than all of the grains of sand on all of the beaches in the world. Well, then they say, more computing time than all of the molecules in the universe. Well, all of the molecules in the universe is way more than all of the grains of sand on the beach. Well, but they're all huge. And no computers exist today that can solve that problem in general. So that got us off the tangent a little bit about deterministic compilers. But we want our compiler to not have to back up, not have to be non-deterministic, And so that causes us to restrict the nature of the grammars that we give to a compiler. That's in essence what's going on.
Fair enough.
Questions? I had one other thing I wanted to give you today that's going to be on the exam, but I also, the quiz is fairly challenging. Uchi.
Before we go to it, question on, you said to test if the grammar is top-down possible, we should check the first set of the language and the follow set in the text. Like how, can you talk more about that or give an example?
Okay, Eric, tell me what he said.
Verifying something as LL1.
Verify, so if it's LL1, so
Oh yeah, I found the eraser for you.
So you found the correct?
No, I found it was 12.
So I got a grammar. E goes to minus E, or paren E, paren, or VT. T goes to minus T, or empty. V goes to AX. X goes to paren E, paren, or empty. Is this grammar top-down LL1 parsable? That's the question, right? All right, so we do first of E, T, V, X. We do follow of E, T, V, X. Minus and paren, and the first of V, minus an empty, A, paren and empty, A, yes? And I have the first sets knocked out. Right paren, minus sign, follow V's in the follow of T. Can T go away? Yes. The follow of V's and the follow of V. The follow of V's and the follow of X. And I claim I have follow sets. Good? Question? Confused? You can do this? Eric?
It's a little confused.
Well, so I did first in follow. I did first in follow. I did first in follow. That was what I got there first. Then I did follow in follow. And then I said, can T go away? Yes. So I did follow in follow. Then I did follow in follow. And that's what I got. Okay, so now your question is the first of minus E intersect the first of paren E paren intersect the first of VT, and then I look at, okay, I don't have to do the follow because while T can go away, V can't. So there's no empty there. And so there's no follow of E that I need to check. So this is the check, and Kevin pointed out, this isn't really written right in terms of actual set intersections. Because we're asking if any one of these have any in common. So if I number these 1, 2, and 3, it's 1 intersect 2, union 1 intersect 3, union 2 intersect 3, and if that union isn't empty, then it's not LL1 parcel. That's what we're really saying, is that all of them cannot have anything in common. Make sense? You with me?
Cannot have anything in common or cannot begin with the same,
I'm sorry?
cannot have anything in common or cannot begin with the same,
Well, the first. The first. So the first of this is minus. The first of this is left paren. The first of VT is A. Now, if V went away, then I'd have to add the first of T. And so I'm creating the first of the string that can't have anything in common. So minus left paren and A, nothing in common, that is parcel.
Isn't the first E going to be minus left paren and A?
But I'm doing the first of this. I'm doing the first of that, who is just minus.
Yeah.
So I don't get to the second symbol unless the first symbol has an empty. So minus, the first of minus is minus. It doesn't go away. So I don't have to think about E. The first of left paren, this is,
Yeah, that was my issue. Sorry about that.
because I'm doing this one.
Yeah.
And so the first of left paren, E right paren, is left paren. Stefan.
And if, say V had an epsilon in its first set?
Yeah.
What if we do,
If-
don't we do the follow-up then E?
So if
V had an epsilon.
If V, now don't get confused if I change the example. If V had an empty, then V's got an empty. Then when I do the first of VT, the first of VT is going to be A, and then since V can go away, then it's going to be minus. And then since V and T can both go away, it's also going to be empty. In which case I don't think about empty, but I think about the follow of E. The follow of E.
Yeah.
Okay? And so the follow of E has dollar sign and right paren in it. So dollar sign and right paren versus A and minus versus left paren versus and so now with adding that empty, it's no longer LL1 parsable. The empty munged it.
What?
The empty munged it because it got us, V went away, and it made us think about the first of T, and the first of T has a minus in it. And so now we got a conflict between this rule and this rule. Because you made me put an empty in there.
There cannot be match at all between all the separables, meaning,
All of them gotta be separate.
okay. Because I thought it would just mean that as long as two of them had the wrong logic.
They all gotta be separate. All of them must have nothing in common. All of them must have nothing in common. Okay?
Can you explain one more time how you got the follow of the, just for some reason, how do you get the lines?
First of T into the follow.
Okay, good?
You were good now.
This is where we're starting.
Right.
We got a few arrows, but we're good with first sets, yes?
Yeah.
We're good with first sets. This is the original example. Now we're going to compute follows. Okay? The first of right paren is in the follow of E. At that little arrow. We just write a dollar in there, and then we write the dollar in there before we start it. Okay? The first of T is in the follow of V. First of T is in the follow of V. Not empties. I will have a stroke if you write an empty in there. And I don't want to have a stroke. Not cool. The first of right parens in the follow of E. The follow of E is in the follow of T. Can T disappear?
Yes.
It can generate empty, so it's as though it was never there. So the follow of E is in the follow of V. The follow of V is in the follow of X. Okay? Follow sets don't contain empty. Follow sets are not empty. Follow sets will never be empty if the grammar is well formed. If I write S goes to AM and A goes to D and B goes to Q, yeah, the follow set of B is going to be empty. Because the grammar isn't well formed, I can't get to B. So B shouldn't exist anyway. And so as long as I can get there and they can generate a terminal string, the follow sets will not be empty. Make sense? Brandon?
When we're computing the follow sets, if we include the epsilon in the set, would you mark that wrong?
Then I'm going to have a stroke and I will mark off 18 points for that question.
18 points on 12.
Exactly.
-6.
18 points on a 3-point question on a 12-point quiz. Empties don't go in follow sets. Again, remember the concept. You don't have to memorize it if you understand what's going on. We're worried about follow sets because we want to know when we replace T by empty. And we're told to replace T by empty by the next token in the input string. that next token in the, you do? Even if you did, it wouldn't accomplish much. Okay, I'm gonna say, I got my program, right? I'm gonna say X is equal to empty. I don't even know how to do that. X is equal to semicolon. Well, that's gonna get me a parsing error. I can't code an empty. So empties can't be part of the terminal string that you're parsing. It can't be part of the program you're parsing. It can't be in a follow set. Brandon.
If I have a string with a space, is that string contain?
Spaces are good characters.
Is it a space or empty?
Yeah, space is a ASCII 40 or 64 or something like that. Spaces are good characters. They're not empties. An empty is a nothing.
So those have double quotes with nothing really.
You read the comics this morning? Beetle Bailey wanted to yell at Sarge. And Beetle says, I'll do it later. And the reason was the sun was shining in this ear and out that ear of Sarge. And so Beetle says, Sarge's head is empty today. So he didn't want to talk to him. That was in the comics this morning.
So, Brandon.
That's a nothing. There was nothing in Sarge's head.
You do that, what is the value of X or your string?
Now that might not be a perfect example because there was space in his head, but spaces are something. A space is a valid character. All right, good. Well, so Ochi asked me. So for this one, the test is going to be the first of minus t intersected with the follow of t for the empty. Right? Makes sense? We did that on Tuesday. Tom?
That's the follow set, not like if there was an A after, like a terminal A after T, that would be, the follow of T would be A, or would that be the entire follow set of T?
Well, it's the follow set of t. You got to compute the follow set of t.
Yeah, I'm just making sure it's the entire follow set.
It's the entire follow set. So this is going to be $paren, and this one's a negative.
Okay.
Yep.
Just clarification, because I thought it was, if any of the firsts evaluates to epsilon, then we have to include the follow of t.
If what?
If it said, I thought the notation was, or the rule was that if any of the firsts that we evaluate, like the first of t, the first of whatever, if that first contains an epsilon, then we must include the follow of t. Not meaning that just because t goes to epsilon, then we have to include the follow of t.
So I think you're asking me two questions.
Okay.
Or maybe not, but I think I'll answer your question. And so if I've got S goes to AB or D, whatever. And so I've got the first of A is equal to A and empty. The first of B is equal to B and empty. Then my question is, the first of AB intersect the first of D. All right, so the first of AB is the first of A, who is A, and the first of B, who is B, and since both can go away, I then have to add the follow of S. I add the follow of S because both of these generated empty.
Correct.
And arguably went away.
Yeah.
But I look at the first of A, that got me the A. I look at the first of B, that got me the B. Then since both go away, I just don't include an empty. I add the follow of S.
Okay.
And so in this question to determine if it's LL1, I'll never have an empty. Even though there are empties in first sets.
Yeah.
There'll never be an empty in this question to determine if it's LL1. LL1, top-down recursive descent parsable. Stephon.
With that union, the intersection of the first and the follow is just gonna be the whole set.
It's going to be the whole set of the
Everything
follow of
okay.
S. It's the whole set of the follow of S. So this is going to have a dollar sign since S is my start symbol. And the whole, all of the characters in the follow of S, all of the characters of the follow of S can't be a D or an A or a B for this to work.
Reason why we include the follow.
Go off 95 and get something that's just.
Celine,
So you're testing the parsability. Do you check each row?
Yes.
Even if it's once it fails.
then you're done.
Okay.
You check all of the grammar rules. Every grammar rule must not have a conflict. If any one grammar rule has a conflict, then that grammar is not top-down parsable. I still can't say your name.
If we have to write out all that, if we look at it and it's obvious that we have two rules.
If you're doing it on a quiz, you got to write it all out because I want to see what you're doing.
So if you wrote first, or like say where you have first A, B, first D, and all of that. So if you wrote A, B, and first D, so it followed at anything from the beginning.
You listening, Cameron?
No.
Just say it again. I can't hear over any background noise, particularly today.
Yeah, just so if you had to, in worst case, write the follow S on that line, like, if you're saying it's not top-down parsable, that's because even with it fully written out, there's some sort of inconsistency there?
No, there's going to be some common character.
Oh, okay, yeah.
So for example, if the follow of S contained a dollar sign and an A, for example, then there would be an A listed here, and now we have a conflict between those two, so we would say, no, it is not parsable.
I know we shouldn't do this, but by looking at it, I know that we should not do this, but by looking at it, is there a way to tell easily that it's not parsable?
There's a way to tell that it's not parsable after you compute the first set and the follow set and then look at all of the intersections.
Okay.
Other than that, you're not going to know for sure. Good? Eric?
So, let's go back. Are we supposed to know about parse trees? Or is this supposed to like more about parse trees, parse tables, parse tables? So, project.
So I was thinking, what are we going to learn about parse tables?
So I claim / I argue that you know everything you need to know now to do project 2. You've got to cruise through all of your grammar rules, left factor them, left recursion them, check them for first and follow sets. These first and follow sets guide your parser. They say, well, if I have an A, then I call AB. So it tells your parser what to do. Tom?
Is there any pseudocode out there for the parser that we can look at just to get an idea of how it's supposed to?
What do you say?
He's saying, is there any documented pseudocode that we can follow for this program?
Yeah. Yeah. In your text, there is a parser written by Loudon for C tiny, or tiny C, which is smaller than C minus. which is smaller than C, which is smaller than C++.
Do you have any idea about where that is?
It's in your text.
No, it's in the back of the book.
So Loudon wrote that. I looked at it,
It's on GitHub too.
I couldn't follow it. So I don't think it's very good.
All right.
What I recommend is through the videotapes and Ron, I pseudo-coded the parser for you. That's all you gotta do. So you've got all of the grammar rules. There's 20 of them or 26 or something like that. So you write function program calls declaration list, declaration, go on, and you just code it according to the grammar. The grammar tells you what to do. And so that's what I did. I wrote this project for a different grammar. But when I was a student like you, I wrote it. And that's what I did. We didn't have even a book as good. I don't even remember if we had a book, actually. Because the faculty who taught it at Missouri University of Science and Technology, that's where I was at, the faculty decided he was going to write his own programming language. He was creating his own programming language. Our class created the implementation of that language, that is the parser. And so he'd give handouts of grammar rules, and we'd have to implement those grammar rules. That part was all fine, except one day I was furious. I was a pretty docile, timid, shy student. Pretty hard for me to say anything in class. For the most part, I just sat there, listened. And I even got yelled at for that. I got yelled at because they said, yeah, you sit there and write down everything that's done and then you figure out what happened afterwards. You're not supposed to do that. Which actually, you all are not supposed to do that. You're supposed to follow what I'm saying. But I couldn't follow everything that was going on, so I wrote it all down and I went home and then I studied and figured out what happened. And so when I got yelled at for that, it was absolutely true. That's what I did. Well, so the faculty came in, he had a scraggly beard. He'd pull on his beard like this, pull, and he'd say something. And he said, well, I found something for my language, and I want you to do these grammar rules and not those. And he says, that won't cause you much problem, right? Threw out 500 lines of code in my program that I had to change and fix for his modification of grammar rules. So I did your project to a fleeting grammar. You're doing this project to a fixed, well-defined grammar. My grammar changed throughout the term. I took this class and database that term. I don't know squat about database. And it was this class that caused it. Well, and it wasn't entirely this class, except I did spend all day, every day working on this class, trying to fix the grammar the way he wanted it. And we had a team of 4 in the database, which is part of the reason I hate group work. It was a cross-listed database class. You know what I mean by that? This is a senior level / beginning graduate level. There could be graduate students in here. So I was a graduate student essentially in an undergraduate database class. Well, so that's okay. So I was with 3 other students. We never met. We never talked. The project's due in a week. Like, hey guys, let's do this project, come on. My role was at the end. I wrote the testing files primarily. I did SQL stuff to test it. I couldn't test it until it was done. I said, come on, guys, let's do this. Nah. 2 days before it was due, I went into the instructor and I said, hey, I'm a graduate student. I can't afford to fail this class, but I can't do this project in a group if they won't do it. So if you'll give me an incomplete, I'll do the whole thing by myself. It was in a fall term. I says, I'll take Christmas, I'll do it all. Let me do it all. The faculty says, let's see how it goes. So the students stayed up all night the first night, all day the next day, all night the next night. They got it done. I plugged in my testing, done. Done on time. I never learned any database. Well, and it's probably okay. I should tell you this to let you know how old I am. Back then, it was hierarchical databases. So we were studying a hierarchical database. And they just mentioned relational databases. Relational databases is what you all do now. So I passed the class. I don't remember what I got, but our project worked. And of course, I passed the test. I studied, so I didn't have any trouble passing the test. But that's why I hate group projects. You gotta rely on the other people who stay up all night. I mean, I was a little older. I was a graduate student. They were 24 years old. They could stand to stay up for 48 hours straight. I had to go to bed. So I think you should just do it. You know, just. Function E. You look at what symbol is your lexical analyzer gave you. You look at the first sets, and you either accept a minus and call E, accept a left paren and call E, except, well, if you're seeing an A, you call B. And then, well, then you accept an A and call X. That's what your project does. Just do it. That's all it is. That's all it is. That's all it is, and it looks simple when you've got 8 production rules. Not as simple when you've got 20, but it's still the same thing.
It's okay. I have like 20 minutes.
What I did when I coded this, and my project worked good. My parser was top notch. My semantics wasn't quite as hot. So if I had S goes to AX or AY, and I had A goes to AM, something to this effect, I didn't left factor. I came cruising in, I said I'm in function S, I'm going to call function A and then kind of figure out where I'm at. So I called function A. See, this is really S goes to AMX or AMY. That's the left factor. But I didn't write that. I just looked at the grammar and figured out what it had to be. So I kept these rules, but I coded this. That makes sense? And what that does, and I'm just making that as a suggestion. If you find that confusing, then do this. This is less confusing. But it also makes the grammar bigger. Now, I wrote it in C. And so, in my view, C is a lot easier than Java. And so my program was straightforward. Tom?
Would it be a bad idea to switch gears and take Java project, try to take that to a Python project? We're at now?
He's asking would it be a bad idea to switch languages in between the projects?
Go from Java to Python.
You can write project 1 in whatever you've written it in, and write project 2 in anything else. So what you do in project 1 is you write all of the tokens into a file. Then in project 2, you switch to a different language, and rather than invoke the lexical analyzer, you just read the file. And you've got your P1 script, in which case it's P2 script now for project 2. So in your P2 script, you execute the lexical analyzer, then you execute the parser as 2 input lines in the script. So you don't have to actually integrate the 2 projects together. Make sense?
So we can write each part of the project separately and just
Yeah. The projects can be totally independent. Make sense? All right. We think we can do this in 10 minutes.
Take
Write a script as far as execute project 1, and that's once it's done, file. I think he goes by points, not by percent. What's the order? If you are.
So you got your recursive descent parser. You sort of understand it. Tom thinks he's okay with it now. Not completely, but so recursive descent parsing is iteration with the stack. Any recursion is an iterative stack kind of program. So I'm now going to show you a parser that isn't recursive descent, but instead literally does iteration with the stack. The step is to build a table. And so I get in my table E, T, V, and X. They label the rows. And minus, paren, A labels the columns. So I have my non-terminal labeling the rows and my terminals labeling the columns. Okay? So my table is going to capture and guide the actions of the parser. And so if I see a minus, I do minus E. If I see a left paren, I do left paren E, right paren. If I see an A, I do VT. And so I'm just guiding the actions, Ron.
Do you need a $sign up there too?
And so if I see a minus, I do minus T. If I see a $sign, I do empty. If I see a right paren, I do empty. Which is exactly the actions of your recursive descent parser. If I do V, I do AX. If I do X, I do paren E paren. If I do minus, I do empty. If I do dollar sign, I do empty. If I do right paren, I do empty. And again, that's just the actions as we've been describing.
Would the empty cells technically be considered failed?
No, the empties, the blanks are failures.
Yeah.
The empties are good. The blanks are failures. Blanks are errors. So if I see a right paren and I'm in V, error. Okay? So now I got my parsing actions. So now I'm going to parse. All right. So what does this generate? Paren A minus maybe paren, I don't know, maybe. So I'm going to parse this. Maybe, I'm going to try to look at the grammar and generate something. Maybe. So I'm going to parse this. I'm going to put my input, paren A minus paren. This is the input. And I'm going to put my stack over here. And so I'm starting out with E. That's the start symbol. And my input token is left paren. So I look up E left paren, and it says replace the E by paren E paren. Okay? Which is what you're doing in your recursive descent parser. You accept a left paren, you call E, ultimately you're going to accept a right paren. But I got it on my stack. All right, so now I've got paren A minus paren. So the parens match, I accept them. Now I've got A minus paren, E paren. So EA says replace the E by VT. And so I get A minus paren, VT right paren. VA says replace the V by AX. A minus paren, AXT paren. The A's match, we accept. So I get minus paren, XT paren. X minus, empty, so the X goes away. Minus paren, T paren. T minus says replace the T by minus T. And so I get minus paren, minus T paren. I took that T off and I put a minus T on. The minuses accept, so I've got paren, T paren, and so I look up T right paren, and it says the T goes away. And so I get right paren, they match. Ron wanted me to put a dollar up here. I should have dollar marking the end of the input and dollar marking the bottom of the stack. So I'll end up with dollar the end of the input, dollar at the bottom of the stack. essentially it says I've consumed all of the input, my stack is empty, it parsed. Make sense? I knew I could do it in 10 minutes. I'll do it again on Tuesday, and then this will constitute all of the material that will be on the exam. So you've gotten a taste of everything at the end of today that'll be on the exam. Eric?
So on Tuesday, you're gonna tell us exactly how to construct the table, because I just saw you construct.
I built the table with non-terminals and terminals. All right? Then I looked at my production rules and I said in row E, I'm going to put in a minus T on the first of minus E, which is a minus. So I wrote minus E under minus.
Oh, okay.
I'm going to put in paren E paren on the first of paren E paren. And so I put in paren E paren under paren. I said I'm going to put in VT on the first of VT. The first of VT was A, so I put in VT under column A.
Oh, okay. Can you repeat that for each one?
And I did it, then I did row T. I said I'm going to put in a minus T on the first of minus T, which is minus. And then I said I'm going to put in empty on the follow of T, which is when we do empties, is on follow sets. Cool? I'll do it again on Tuesday. In case I'll have another. Okay?